While the datasets to which people want to apply machine learning keep getting larger, so does the computing power. Today, it is not uncommon for people to train a single machine learning model using multiple workers, each of whom deals with their own data partition. In this distributed setting, each worker calculates the gradient on their own data batch. Then, the model is averaged across all workers, and this process could then be repeated millions of times. Averaging models across all workers seems simple, but it is often the system bottleneck for distributed training. Consequently, how to do this efficiently has been studied extensively. Here are two popular ways in which most distributed deep learning systems are averaging models. Let's say you want to average 4 models from 4 workers. In one approach, we could send all models to a single server and have the server average them and send the average back. A second, smarter way of doing this is to use an all-reduce operator. The idea is simple. If all workers communicate via a ring topology, let the model flow through all workers, doing the sum for each, and then let it flow through all workers again. Both these centralized approaches require the information from a single worker to reach all other workers. But is this necessary? Not really, because there is a decentralized alternative. Let's stick to the ring topology. What would happen if, with every iteration, instead of averaging all models across all workers, we average the model of a single worker with its 2 neighbors? People have known for a long time that this decentralized approach will converge, and thus, this technique has been used as a compromise when centralized communications are difficult or expensive. This brings us to the technical contribution of our paper. How does the decentralized approach compare to the centralized approach? Surprisingly, we find that after we ran a large enough number of training iterations, the decentralized method has the same convergence rate as the centralized one. In addition, because the communication overhead of the decentralized approach can be lower, decentralized communication can be faster, even when centralized communication is possible. In other words, what used to be a cost-saving compromise could become an optimization technique. To our best knowledge, this is the first theoretical analysis showing that potentially a decentralized training algorithm could beat its centralized counterpart. We tried out this idea by training a convolutional neural network with up to 100 GPUs. As you can see, decentralized training achieves almost the same convergence rate as centralized training, and when the network gets slower, decentralized training can be significantly faster.